Hello there. It is 8:11 p.m. on a Friday, and so that means it is time for sections 1, sections 2, sections 45, I don't care, of econometrics. So let's get to it. Let me show you my new setup. All right, so welcome to my home. At least for this week when I'm making this video, there's not going to be a baby screaming. Can't say there won't be next week, but we'll roll with the punches, cross that bridge when we get to it. I hope everyone is doing well. I hope people are somewhat settled. I look forward to hearing from you guys soon. This has been an absolutely crazy week. What is this video? This is going to be a video about omitted variables bias. It's the topic that we covered just before all of this craziness started. In that sense, it's an optional video. You don't have to watch it. It is a little bit for me to debug this whole video online digital lecture thing. This is the fourth time I'm making the video. The first time, the video didn't work. I didn't share my screen. The second time, I forgot to unmute my microphone. And the third time, I couldn't find the pen to my whiteboard. So sometimes the problems were slightly more technical than others. Sometimes it was more just idiocy. So, I'm going to do a little recap on the whiteboard, then I'm going to do a little recap on the computer, and that'll be it. My goal with these videos is to make them pretty dang short, or as quick as they can be. I'm not going to repeat myself as much as I do in other lectures, and the reason for that is you guys can stop, you can pause, and so I'd rather say it once the clearest way rather than saying it 3 or 4 different times and kind of extending the length of the video. So with that, I'm going to have my cameraman pan over to the whiteboard. Thank you, cameraman. And we are going to talk about omitted variables bias. I know that my mouth might not always be visible, but hopefully you can still hear me. So omitted variables bias is the most common OLS assumption violation that we have. It plagues almost every cross-sectional or time series regression, especially if you don't have randomly assigned independent variables, which we rarely do. We're usually using what's called observational data that we gather from the world, and it's hard to experiment on humans or businesses and have randomly assigned things. So it's a very common assumption, and we're just going to redefine it, even though we did it last class. We're going to assume that there's some outcome. I'm going to use the example of wages, and that in truth, wages, you need 2 independent variables to describe wages, that you should have 2 variables in your 2 explanatory variables in your model. So yi equals beta naught plus beta 1 x1i plus beta 2 x2i plus an error term. And I'm going to call this beta 1t. In other words, this is the true beta 1. This is what we wish we could estimate. And then there's what we observe. And what we observe, we're going to assume that we only observe x1, that we don't observe x2. And so maybe y is wages, and x1 is whether or not someone's good looking, and x2 is experience. And we know old people are ugly, so that'll cause bias. Maybe y is wages, this is education, and x2 is ability. That's maybe the most classic example of this. So what we observe is yi equals beta naught plus beta 1, and I'll call this beta 1 OV for omitted variable, x1i plus the error term. And now kind of skipping the math that I did in class and that you can see in the textbook, the punchline takeaway is this: if we estimate this model, this estimate of beta 1 of the causal effect, say, of education on wages, is going to be biased by the fact that we have omitted an important other variable, say ability. We might not know the exact magnitude of the bias, but we are going to be able to define its sign and define kind of what the shape of the bias is. And so the bias formula is that the expected value of beta 1 OV hat, what we expect to estimate in this observed model is the true causal impact of education on wages, or whatever slope it is we're estimating, plus beta 2 times alpha 1 hat, where beta 2 is the beta 2 from this model, the impact that the omitted variable would have on the model, on the outcome, and alpha 1 hat, which is the relationship, sort of the slope of the relationship between x2 and x1. You get this if you ran a regression where x2 was the outcome and x1 was the explanatory variable. This here is the full omitted variables bias formula, and then this second term is referred to as the bias term. Beta 2 times alpha 1 hat. Now, of course, in a model where maybe you had 5 explanatory variables and the omitted one was the 6th variable, this would actually be beta 6 or something. We use beta 2 kind of because in our examples we tend to think about a model with 1 included and 1 excluded variable, but it extends to more than that. And what we can do is we can ask ourselves, what should the sign of this bias be? Should it be positive or negative? And to get that answer, we need to ask ourselves 2 questions. 1, what is the expected sign of beta 2? In this case, if x is education and x1 is education and x2 is ability, we would expect that ability would be positively correlated with wages. And what do we expect the correlation between between education and ability to be? We also expect that to be positively correlated. So what that tells us is that if we run the observed model, if we estimate beta 1 hat without x2 included in the model, what we're going to estimate is the true causal effect of education, beta 1t, plus a positive bias, which is to say what we estimate is going to overstate the importance of education because it's going to sort of combine the true impact of that education has on wages plus the impact that ability has on wages. All right, and with that, we're going to go to the computer. So I have my cameraman pan back over here to me being seated. Very good. So I'm going to go here, and then I'm going to go ahead and share my screen. With you guys. All right, and so this table, we're going to be filling this table in as the semester goes on. I'm going to post it on Moodle. You probably can have access to the full table. There's a similar one in the book, but I kind of like the process of going through kind of now that we've talked about one of the violations and filling in each of the categories of things that I expect you to know about it. So first of all, omitted variables bias violates assumptions 1 and 3 of OLS. Assumption 1 is that the model is, ooh, I just touched my face. Not supposed to be doing that. Sorry, don't tell my wife. Assumption 1 is that the model is correct and linear. And in the case of omitted variables bias, that assumption's wrong because there's an omitted variable. There's a variable that should be in there that isn't. And assumption 3 is that independent variables are uncorrelated with the error term. And as we just saw on the board, that assumption is also false because the omitted variable, which is a part of the error term because it's not included in the model, is in fact correlated with the included x in the model. So the definition of omitted variables bias is that there is correlation between x and the error term, and the definition of the bias itself is beta 2 times alpha 1 hat. Anytime we violate an OLS assumption, there's going to be a consequence of doing that violation. In this case, the consequence is that our slope estimate is wrong. We get biased estimates of the relationships between x and y. And for each OLS violation, we're going to have a method of detection. So in this case, detection usually is based on theory. Usually we have omitted variables bias because we don't have access to the omitted variable that we wish we had access to. So understanding when and why you have omitted variables bias really comes down to good, solid understanding of the process of the outcome variable that you're studying. If it's the case of wages, you need to understand how wages are created. If you're studying housing prices or restaurant sales, then you need to really think about, okay, how do restaurants generate sales? What does go into the price of a house? So when it comes to detection, typically it's detected based on theory because usually we don't have the omitted variable itself. How do we correct for omitted variables bias? For some of these violations that we get throughout the semester, we're going to have pretty clear, easy ways for how to correct for it. Just a simple extra thing you do to the regression, an option that you put into Stata. This is not one of those cases. Correcting for omitted variables bias usually is not possible because usually it's the variable's omitted because you don't have it. And in that case, the best you can do is hypothesize the sign of the omitted variables bias. you take the slope that you have and you say to yourself, do I think this is a upward bound or a higher bound on the true slope? Do I think it's a lower bound? Do I expect the true coefficient to be bigger, smaller, higher, lower? And then in the other category, I'm just going to add in that I think that understanding omitted variables bias and detecting it and understanding kind of what it means for when results are closer to causal or closer to correlational is one of the hardest skills to acquire in this class. And so I'm going to be asking you guys to practice it a lot going forward. All right. And so now I'm going to switch over to data. That was all my stuff from, let's say, 10 attempts ago at this video. So let's clear it and restart. All right, so I'm going to go ahead and load the data set on wages and beauty that was used in the hammer mesh video that I showed in class and that you're going to be doing your lab on in maybe, well, it depends on when you watch the video, but that you'll be doing a lab on. So this data set, the main outcome variable here is wages. An observation is an individual person, and the data set contains information on these people's education, their experience, the health, their attractiveness, whether or not they're married, whether or not they live in a big city, or they live in the South, whether or not they work in a union. So in class, I did the example where old people are ugly, and I looked at the omitted variables impact on the looks variable. Let's look at something different in this video. So let's look at the consider omitted variables bias when it comes to estimating the impact of living in a big city. So to start, let's regress living in a big city on your wage. Do you expect that to have a positive or a negative coefficient? So what we get is a positive coefficient. I'm guessing that's what most of you would have guessed. Wages tend to be higher in big urban areas than in less populated rural areas. And so now what we're going to ask ourselves is this impact of big city, saying that living in a big city raises your wage by $1.8 per hour, is that a causal effect or more correlational? Is that estimate subject to omitted variables bias? And the answer here is probably yes. If there were no bias, what that would mean is that for the average person not living in a city, if we kept everything else the same, if we kept their education levels the same, if we kept their skill sets the same, and we brought them to a city, that they would be making $1.8 more per hour on average. However, it's likely the case that we're not comparing apples to apples here, that people who tend to live in a big city tend to be different on other dimensions than people who don't live in a big city. One of those dimensions might be education. We would expect, or at least I would expect, that education would be positively correlated with people living in a big city. We can check that quickly by doing regress big city, or let's do regress education on big city. All right, sure enough, they're positively correlated. People who live in big cities on average have an extra year of education. And so we also expect education to be positively correlated with wages. So if beta 2 is positive and alpha 1 hat is positive, what that means is that we believe that this 1.88 estimate is probably an overstatement of the causal impact of living in a big city. That this estimate is both picking up that cities pay more, but also that more educated people tend to live in big cities. And so if we control for education, we're expecting the coefficient on big city to go down because the one without education is an overestimate. So let's look at that, regress wage on big city, and now we control for education. And so the number we get, we're going to compare to 1.88. And sure enough, what we get is 1.54, about 20% reduction in the coefficient on big city. So that confirms what we thought all along, that without controlling for education, we'd be overstating the impact of living in a big city. You have a lot of other variables here that you can think about. For example, do you think that that marriage is correlated with living in a big city? Does omitting marriage bias the effect of living in a big city? Does the impact of looks bias the effect of living in a big city? Belonging to a union? Ask yourself those questions. You can play around with this data set, and as you add and subtract different control variables, you should find that you start to get a sense that you're able to kind of predict what's going to happen to the coefficients before you even run the regression based on the expected relationships among all of these variables. Okay? Um, all right, so that's it for the omitted variables lecture. Um, like my channel, subscribe, tell me what's up in the comments. And that's somewhat in jest, but also please do tell me about the audio, the video quality, and whether or not I'm talking too fast, whether you'd like more examples, less, and all that kind of stuff. So anyways, hope all of you are doing well. Talk to you guys soon, and take care.